Hello everyone, Professor Hoffman with you. I wanted to talk about a couple of topics that are going to be on your final. Two of the main chapters that we're looking at for the entire class of Introduction to Meteorology is Chapter 4 and Chapter 9. Chapter 4 is about moisture and atmospheric stability. And basically what that is looking at is how does air rise, how do we get condensation, and then how do we get precipitation. So remember, there are four ways to get air to rise. The one major one that we've talked about through the semester is frontal wedging. A front, warm front, cold front, occluded front, dry line, stationary front. Those are the things that we're going to be looking at. So that was the focus of Chapter 9, and we tied into the information from Chapter 4. So again, you need moisture. Remember saturation, relative humidity near 100%. You need the temperature to cool down to its dew point. When the dew point and temperature are equal, that's when you have saturation. Well, what is one way to do that? Cool the temperature. How do you get the temperature to cool? Well, air will rise. As air rises, it cools and expands to its dew point, and then you get condensation, which leads to clouds. So one of the things that we focused about in Chapter 4 about that atmospheric stability is, I'm going to scroll down to the bottom of the page here. Don't forget there are other topics there. And we've talked about air rising. Dry adiabatic air rises and cools at a rate of 10 degrees Celsius per 1,000 meters. And it also compresses and warms as it comes back down at 10 degrees Celsius per 1,000 meters. But when the air is saturated or wet, this rate of cooling changes. That would be 6 degrees Celsius per 1,000 meters as it goes up. And as it comes down, it warms at 6 degrees Celsius till it gets to its lifting condensation level, and then it warms at 10 degrees Celsius per 1,000 meters. All right, so again, we have the four methods of getting air to rise. And then one of them that we focus on, especially in Chapter 9, is frontal wedging. How is that air being forced up? How is that air cooling and expanding? So remember pages 96 to 105, and these charts are on page towards 100 and 103, atmospheric stability, conditionally instability or conditionally unstable, and absolute instability or absolute unstable air. Okay, so the first one I'm going to focus on is this absolute instability. Okay, so let's take a look what's happening. You guys all remember this chart. We drew the diagrams. On the left-hand side, that is the temperature of the environment. Remember, we use that to figure out the temperature of the environment, the environmental lapse rate. So take a look with me here. So notice at the surface temperature will be a given. In this case, it's 20 degrees Celsius. Your environmental lapse rate here is 5 degrees Celsius per 1,000 meters. So what does it tell us? Well, for every 1,000 meters we go up in the atmosphere, the temperature will drop by 5 degrees Celsius. And you can see that going up 10 degrees Celsius here, 5 degrees Celsius here, 0 to -5. So in this particular case, when the environmental lapse rate is 5 degrees Celsius per 1,000 meters, that's telling us the rate of cooling in the atmosphere. So all you're doing is subtracting from the surface temperature 5 degrees Celsius for every 1,000 meters you're going into above the ground. Okay, so we go from the surface to 5,000 meters. You can see in that time frame, -5, -5, -5, -5, -5. So that's the first thing we need to do, figure out the temperature of the environment. And again, you'll be given the surface temperature, you'll be given the temperature of the environmental lapse rate. Now we need to figure out the air parcel temperature, okay? So the air parcel temperature, we will be having it given here, the given surface temperature. So just like over with the air temperature, it will be 20 degrees Celsius. So the surface temperature and the air parcel temperature will always be the same. The one thing that we do need to watch is where is the condensation level. The lifting condensation level is where we have saturation. That condensation level will also be a given. In this particular case, that condensation level is at 2,000 meters. So that tells us everything above 2,000 meters is cooling at a different rate. And that rate is 6 degrees Celsius per 1,000 meters. So here you have your air parcel temperature. So this is all dry down here. This is dry air. So at the ground, when the air is dry and it cools and expands, it's going to do at a rate of 10 degrees Celsius. So that's how we go from 20 to 10 to 0 in dry air. Now the air becomes saturated around 2,000 meters. So now he starts to subtract by 6. So that's how you get -6, -12, and -18. So that's how we find out the air parcel temperature. Now to find out if this atmosphere is stable or unstable, okay, what we're going to be looking at is we compare the air parcel temperature, this temperature over here. We compare these temperatures with these temperatures over here. So if this side is colder than this side, okay, the air is stable. So if your air parcel is cooler or colder than the environment, this is said to be stable and air wants to sink. Sinking air is not conducive to more clouds and precipitation. So this is considered a stable environment. So this is a stable environment, okay? So hopefully you understand that. You're comparing the environmental lapse rate. You will have a given of the surface temperature. Your environmental lapse rate will be given, okay? Your lifting condensation level will be given. And then you have to figure out the temperatures at all the different levels. Let's do another one here when we look at an unstable air mass or instability, okay? You can see your surface temperature. That will be a given. Surface temperature in this particular case is 40 degrees Celsius. 40 degrees Celsius also for the air parcel. Remember, the surface temperature is a constant for your air parcel and the surface temperature. So let's take a look what we're having here. Okay, so let's start out with the temperature of the environment. So your surface temperature is 40 degrees Celsius. In this particular case, the environmental lapse rate is 12 degrees Celsius per 1,000 meters. Your condensation level, once again, is at 2,000 meters. So again, the environmental lapse rate, it tells us the rate of cooling in this particular situation. So from 40 degrees Celsius, we subtract 12, we get 28. 12, we get 16. 12, we get 4. Another 12, we get -8. So the environmental lapse rate will help us tell us the exact temperature of the environment at different levels. Okay, so the environmental lapse rate's a given, the surface temperature is a given. Now we look over to the air parcel. So your air parcel, again, starts with 40 degrees Celsius. In this particular case, dry air, which is below the condensation level, cools at a rate of 10 degrees Celsius per 1,000 meters. So as you're going up, -10 gives us 30 degrees Celsius. As we're going up, we get to another -10, which is 20 degrees Celsius. Now the rate of cooling now changes. Up in this location, the air is said to be wet or saturated. So when the air is wet or saturated, it now cools at a rate of 6 degrees Celsius. So at the condensation level, the air is still dry. Above the condensation level, the air is now wet. So that's how we go from 20 to 14, we subtract 6. From 14 to 8, again, we're subtracting 6 for every 1,000 meters we go up. Now we need to compare the temperatures here. So this 8, 14, 20, 30, that is the air parcel temperature of the atmosphere. We need to compare that with the actual temperature of the atmosphere. When the air parcel is warmer than the environment, the air wants to rise. So when the air rises, that means the air is unstable. So at each one of these levels, the air is unstable. So this is an unstable environment. Instability. Air wants to rise at levels, at all these different levels, of 4,000, 3,000, 2,000, 1,000. So the air is rising. That is unstable condensation and precipitation. So that's what we're looking at when we were talking about rising air. What happens? If the air parcel is warmer than the environment, air wants to rise. If the air parcel is colder than the environment, the air wants to sink. Now, when you take measurements of the entire atmosphere, okay, and you're comparing each one of these different levels, if you have a change through all different levels, the atmosphere is called conditionally instability or conditionally unstable, where part of the atmosphere is stable and part of the atmosphere is unstable. How do you find that out? You have to do many different layers. Now, I may ask you at an individual layer. So, for example, in this particular case here at 5,000 meters, the environment is, the rising air is warmer than the environment, so this is unstable. But down here, the rising air is cooler than the environment, it's said to be stable. So you have to measure all different levels. Now, this entire environment is conditionally instability or conditionally unstable. But at each individual level, you have some that is unstable and some that is stable. And again, the given would be the surface temperature, the environmental lapse rate, what is your condensation level. Down here, your condensation level is once again 2,000 meters. So please take a look at Chapter 4, understand where the air is stable and where the air is unstable. You have the different videos there. So now that's recapping Chapter 4. I want to jump into Chapter 9. Okay, so now that we know that air is unstable and air rises, where do we have the best threat of rising air? Well, a front. A front's going to push air up. It's going to cool. It's going to expand. Condensation, you have clouds. So where are you going to have clouds? Along the front. Okay, air is going to rise along the front. So this was on chapter exam 4 from chapter 9. There's going to be a similar to one like this on the final, and understanding what happens at all the different points. Where you have warm air, where do you have cold air, where do you have clouds? So just like on chapter test 4, exam 4 from chapter 9, understanding what happens at each one of these points. What's the air mass? What's the wind? What's the pressure? Okay, is it rising? Is it falling? Is it staying the same? Remember what happens before, during, and after a front. So again, when we look at different parameters here, okay, at point A, certain things happen. So at point A, and we're looking towards point B, you're going to have some high clouds down to low clouds. Right now at point A, there are no clouds, but looking on the horizon towards point B will have clouds. The type of clouds they have at point B, nimbostratus or stratus clouds. That would be this down here. Okay? Low clouds, it could be rain. If this was winter, it could be snow. Okay? So at point A, you're looking westward, you're starting to see high clouds to low clouds. Your winds over here are again, southeast to easterly, okay? Generally looking at southeast to easterly winds over here. You do have a change now over towards C. Now that you've passed the front, you're now in the warm air. At C, here you go. If you have clouds at point C, you would have some cumulus clouds. Great spot for barbecue, warm weather, going to the pool. This is where you're going to find the warmest air and the most sunshine. Maritime tropical air mass around point C. Winds are southwest to southerly this direction. Now at point D, ahead of the front, that's where we have the clouds. Best chance of thunderstorms, tornadoes, winds, south-southwest. Pressure is falling ahead of the front. Pressure is rising behind the front. Warm maritime air mass at D. Now we go over to point E. Skies are clearing. Winds west-northwest. Dry, cooler air. Continental polar air mass. So understanding what happens along each one of these points. What is the wind direction? The highest dew points and the highest temperatures would be at point C and D. The highest temperature most likely is point C because there's generally less clouds and it's not raining there. Maritime polar air mass ahead of the front. Point F has those east to southeast winds here. Here are your clouds. If I were to put a point on the last test, this was 0.5. So in this location along the front, you have low clouds, nimbostratus clouds. If this was winter, this is where your best chance of snow would be, just north of the low. Now point G is continental polar air mass and it's starting to dry out. It's at the edge of the cloud cover, okay? So that's one of the things that we would be looking at, the edge of the cloud cover at point G, okay? And the clouds would start to dissipate behind point G. So understanding with this mid-latitude cyclone, where would you find thunderstorms? Where would you find low clouds? Where's the coldest temperature? Where's the warmest temperature? Okay? Again, over maritime polar, cool, cold air, the coldest temperatures would tend to be back towards point G. Colder or cooler, E is compared to D. So E is going to be colder than D. The warmest spot in this location would be point C. And again, counterclockwise wind flow. Wind is moving into low pressure. Here's your occluded front. Okay, here's your cold front. Here's your warm front. Understanding all the different things that are happening at each one of these points. Again, go back and watch the videos in Chapter 9. And then just a recap of Chapter 11, hurricanes. Understanding where the hurricanes form, how do they form, what are the ingredients that you need for a hurricane. Remember, you need really warm weather. Hurricane Category 1 starts at 64 knots or 74 miles per hour. And again, the Saffir-Simpson scale, understanding what happens with the wind speeds, Category 1, 2, 3, 4, and 5, okay? Tropical systems are cyclones. They start off as a tropical wave. They go to a tropical depression, which has winds of up to 38 miles per hour. Tropical storm gets a name at 39 miles per hour and 74 miles per hour for a hurricane and 111 miles per hour for a major hurricane, which is Category 3. So understanding the structure of the hurricane as well. So these are just some of the topics that